So before starting this video, I'd love to thank Reliable for sponsoring this entire tree series. Did you know that companies like Google, Apple, Starbucks are now hiring people without any degree or experience? Why? Because they believe that skills are more important than anything else. Now, top companies in India, like the top startups, have also started following this trend by hiring through a platform which is Reliable, which is backed up by an academy. All you have to do is to give the Reliable test, and based on your score, this platform send your candidate profiles to 50 plus companies, which includes Cred, Upgrad, Vedantu, Razorpay, etc. And you can get selected for a job role within a week. Another amazing thing about Reliable is it's absolutely free. So please make sure you check out the links in the description. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving finding the maximum width of any given binary tree from the FreeCut tree series. So let's take this first binary tree as to be the second binary tree and the third binary tree, and let's understand the term width of a binary tree. Now when I say width of a binary tree, so what is the definition width? It basically is the number of nodes between any nodes, between any two nodes. That is what is like the maximum number of nodes in a level. If I just write the definition in a much better way, it'll be maximum number of nodes in that particular level between any two nodes. So when I say maximum width, so it is basically among which two nodes on a same level do I have the maximum number of nodes. So let's take this first binary tree as the example. So I can say that the width of this binary tree is nothing but 4. Now you'll ask, why is this 4? Very simple. If I consider this level, yes, this is one node, this is another node. Like just imagine there would have been a node, like if it has a left, it would have had a left node, then this was one of them, and then this. So the maximum width in any level of this binary tree 1 is 4. So I can say maximum width of this binary tree is 4. Let's consider this example. So over here, I can say that the maximum width of a binary tree is 2, because if I consider this level, over here I have 1, over here I have 1, so it's 2. I cannot take this because this is a node, but on the right I do not have any node. Remember, between any two nodes, so this was one node here, this was one node. So between these two nodes, the number of nodes that is practically possible, that is what I call as width. So let's understand this binary tree 3. Pause this video and think what can be the width of this binary tree. And if your answer is 8, then you're correct, or else you are wrong. Now you might ask, why is it 8? It should not be 8. So let's draw this imaginary, like just in case if these two nodes would have had nodes in between them, how does that look like? This would have had an imaginary node in between. This guy would have a right. This guy then would have here, would have a node here. This guy would have had a left, and this guy would have had a left and had a right. And this 4 would have had a left. Like imaginary had this binary tree 3 had nodes on every node, like left, right on every node, and this is what it would have had. So on this level, what's the number of nodes it could have between 7 and 6? I can be like, it is 1, 2, 3, 4, 5, 6, 7, 8. So width is the number of nodes in a level between any two nodes. So hypothetically, there could have been 8 nodes if I start from 7 to 6. So I can say that the maximum width of this binary tree is 8 indeed. So if I'm looking to find a width and the maximum width, which traversal should I follow? The width is dependent on the level, right? So I can say it's basically the number of nodes between the first node in that level and the last node in that level. Like ideally I can say this. So if I'm looking for the first node and the last node in a particular level, which traversal should I think of? I should definitely think of something which is level order traversal, right? So that's the first thing that comes to your mind, that we should definitely follow the level order traversal in order to get the maximum height. Now, this is the tree that is given to you. Every node has any random value. But don't you think if the tree was indexed in such a way that this guy was 1, this guy was 2, this guy was 3, this guy was 4, this guy was 5, this guy was 6, this guy was 7, this guy was 8, 14, 15. So in case I could have, like just in case, if I can index the tree like this, don't you think the question becomes very, very simple? Indeed, because what I need to do is go to every level, pick up the first node, like on this level, pick up the first node index, pick up the last node index, and yeah, just subtract it and add a plus one. I just need to subtract it and add a plus one in order to get the width. That is what I need to do. Again, go to this, take 8, take 15, 15 minus 8 plus 1, that's 8 nodes in between them. So, if I can index them, yes, if I can index them such that I can easily, like, just because of the indexing, I can easily subtract. Now, you might ask, will the indexing depend? Like, what if these nodes are not there? Like, we saw an example where we had something like this, right? Like in our binary tree 3, we had something like this. In that case, will we index it like 1, 2, 3, 4, 5? No, we're going to index something like this only. Like this will be 1, this will be 2, this will be 3, this will be 4, hypothetically this will be 7. Like I know there is no nodes in between, but we're going to index it in such a way that it holds its value. Okay, hypothetically there should be some nodes here, but there are no nodes, but still I'm going to index it in the proper format. So if I can index it, then my question becomes very simple. In any level, the first index minus the last index, like minus the last index plus 1 in any level, the maximum value of this across levels will be my answer. So the question boils down to a very simple question where I just have to index every node. So the indexing is very simple. Now, since we know that like the binary tree is something like it has two nodes at maximum. So what we will do is, if we are indexing this as 1 or 0, let's assume we are indexing this as 0. So there are like couple of kinds of indexing generally we do. If it's a 0 based indexing that we start off with, and if we're considering a node which is having an index I, the left one will always have an index 2 into I, whereas the right one will always have an index 2 into I plus 1, and the right one will always have 2 into I plus 2. This is when we consider 0 based indexing. If you're considering 1 based indexing, then if this node is having I, then the left guy will have 2 into I indexing, whereas the right guy will have 2 into I plus 1. Okay, that's what it will have if it's a 1 based indexing. So if I'm taking 0, the left guy will have 2 into 0 plus 1. So this becomes first index. The right guy will have 2 into 0 plus 2. So this becomes 2. For here, the left guy will have 2 into 1, that's 2, plus 1. So this becomes 3. 2 into 1 plus 2, this will become 4. 2 into 2 plus 1, this becomes 5. 2 into 2 plus 1, this becomes 6. Similarly, 2 into 3 plus 1, this becomes 7. This will become 8. This will become 9. This will become 10. This will become 11. This will become 12. This will become 13. This will become 14. So this is how you can do the 0 based indexing. Again, you could have done a 1 based indexing also. So this is how, even if you do not have these nodes, like if you do not have these like just imagine these nodes are not present, then also the indexing will be maintained if you follow this format. Now if you might ask, how does this intuition come in? It's a very simple, like this is generally used in segment trees. That is where from this comes in. This is used in segment trees from where this logic comes in, and it is solely dependent because this node has two nodes, and after that we have again two nodes. So that is the reason this 2 into wala stuff works. Okay, so we have pretty much done this. But is this the answer? No, this is not the answer. Why? Let me give you a case where this will fail. Like if you follow this 2 into I plus 1, 2 into I plus 2 methodology to assigned indexes, it's gonna fail. Why? Let me tell you that. Now imagine this guy is 0 and you do not have any other tree. It's a skewed tree. So the left guy will definitely have 2 into 0 plus 1 becomes 1. This guy will have 2 into 1 plus 1, so that's 3. This guy will have 2 into 3 plus 1 becomes 6. This guy, the next guy will have 2 into 6 plus, I hope you're understanding what I'm saying. If it's I, this becomes 2 into I, correct? And the next guy will become twice of this, realize this, twice of this plus 1, right? So you're increasing it by twice, by twice, by twice. So don't you think if it's a skew tree and this length, assume like it's a worst length of 10 to the power 5, like the entire length of the tree is 10 to the power 5, the number of nodes is 10 to the power 5, don't you think the twice increase will be a lot more and it will be an overflow? Indeed, it will be an overflow, because if you keep on doing twice of this, like it's going to be 2 to the power somewhere around 10 to the power 5. That's going to give you an overflow, because next time it will be 12, then it will be 24, 25 around, then it will be 50. It's going to increase and it will end up giving you overflow. So that is the reason we cannot exactly use something as I and 2 into I plus 1 and 2 into I plus 2. We need to modify this in order to prevent overflow, and I'm going to tell you how will you modify this. So in order to prevent overflow, what we will do is, if this is 0, right, this is going to be 0, so this is definitely going to be 2 into 0 plus 1. This is also going to be 2 into 0 plus 2, so that's 2. Now in the next level, when I start giving these numbers, ideally this should have been 2 into 1. I repeat, 2 into 1 plus 1, that's 3. This should have been 4, this should have been 5, and this should have been 6. Instead of this, yes, instead of this, I will try to have it as 0, 1, 2, 3. Again, over here, ideally, this should have been, like, ideally, it should have been 7, 8, 9, 10, 11, 12, 13, 14. But instead of that, I'll try to have this as 0, 1, 2, 3, 4, 5, 6, 7. So you'll be like, how will we do that? So in order to reduce this overflow stuff, what we will do is, now when this node was having a value 1, this had the left as 3, this had the left as 4, right? What if instead of 1, I try to make it 0, and then the left guy will have a value 1 and 2. So what I'll do is I'll try to convert this into 1 and 2. And I'll try to convert this into something as 3 and 4. That's what I'll try to do. So how can I do that? So if I can convert 1 to 0, then I'll get this 1 2, right? Ideally, this 2 should have got 5 and 6. But I want something as 3 and 4. So if I can convert this 2 into 1, then I think my job is done. I'll get 3 and 4, right? So can I say whatever is the minimal in this level, that's 1. I'll do 1 minus 1, 0, and then I'll get the left children and the right children according to the formula of 2 into I plus 1. And similarly, I'll do 2 minus 1 equal to 1, and then I'll get the left children 3 and the right children 4. Similarly, if I take this 1 and I do 1 minus 1, I'll get 0. Then the left children will become 1 and the right children will become 2. This 2, I can do 2 minus 1 equal to 1, and then the left children will become 3 and the right children will become 4. Similarly, this will become 3 minus 1, 2, and the left children will become 5 and the right children will become 6. Similarly, this can be made 4 minus 1 equal to 3, hence the left children will become 7 and the right children will become 8. So can I see that if I do this change, I'll end up making everyone, like I end up making everyone in terms of 1, 2, 3, 4. And if I want the next children's, that's very simple. 2 minus whatever is the minimal. This will be your value of I for getting 2i plus 1 and for getting 2i plus 2. That's going to be your value. You can easily compute I. So I think I have solved the issue of I think I've solved the issue of overflowing. I think I've solved the issue of overflowing. If there is a I, just make sure you make I equal to I minus whatever is the minimal value on that level. And after that, once you've got I minus minimal, treat this I to get 2 into I plus 1 and 2 into I plus 2. And after that, it's very simple. On every level, take the minimal, like take the leftmost guy, take the maximum index and just subtract it, and plus 1 will be your answer. So in order to solve this problem, we are going to do a level order traversal. So what we will do is we'll take a queue data structure and we're going to store a pair. So first I'll store the root of the tree as well as the index that we're going to start off with. So I'm going to start off with the 0th index. So I'll store 1 comma 0. So initially when I start off with this, I have a single node in this level. So I'll just pick up this entire stuff. So I have the node 1 with the level, with the index 0. So since I have one node, can I say that my width as of now, yes, my width will be, the maximum width that I can have is 1, because this is the first guy itself and this is the last guy itself. And if you remember, the formula was very simple. The last index minus the first index plus 1. Since the last guy and first guy are equal, they'll cancel off each other and I'll have plus 1. So the width is 1, right? Now what you need to do is you need to get the left guy. Who's the left guy, guys? The left guy will be 3. So you take that 3 and will be the index. The left guy will have an index of 2 into 0 plus 1. That's 1. So 3 comma 1 will go in. The right guy will have an index of 2 into 0 plus 2. So 7 comma 2 will go in. That is what I'll enter into the queue data structure. So once I'm done with this, this is done. Next time I'll do the next iteration on the number of nodes available in the queue. So basically I have 3 comma 1 and I have 7 comma 2. So I can say this guy, since we are doing a level order traversal, this guy will be the leftmost guy with the index 1. This guy will be the rightmost guy with the index 2. So since I know the formula is last minus first, so 2 minus 1 plus 1, that means a width of 2. So the width of 2 will be, like, we will increase the width to 2 because we got a width which is better. Now for 3, which is the left guy is 8. The right guy, we do not have a right guy. So if you remember, we will not consider 1. Instead, we will take 1 minus 1 equal to 0, so that we do not have an overflow. So 1 minus 1 is 0. So this guy will have 2 into 0 plus 1. So 8 comma 1. So indexing will start from 1. So I will have something as 8 comma 1. So the right doesn't have, like, we do not have a right. So let's have, for this guy, have a left. So this will be 7 doesn't have a left. So let's have a right. So when we have a right, we have a 4 comma, what will be the index? Again, we will not consider 2. Indeed, we will consider 2 minus 1. Yes, whatever is the minimal on this level, like minimum index is 1. So we'll take this and we'll get a 1. So 2 into 1 plus 2 is right? So that's going to be 4. So you're going to take this. So over here, we will have 4 comma 4 as the next. So again, this level is done. So I can say that this level has been completed. So in the next set of iteration, we will take the next set of nodes that are in the queue. So I will have an 8 comma 1 and I'll have a 4 comma 4. So if you can see that this was indexed as 1 and this is indexed as 4. So you have made sure that we do not have an overflow, because always the indexing is starting from 1 and going till 4. So if you have an 8 comma 1, we do not have a left, we do not have a right. Similarly, we do not have a left, we do not have a right. So nothing new will come. And in order to get the width, you'll take the minimal guy, that's the first guy, which is 1. You'll take the last guy, that's over here 4. 4 minus 1 is 3 plus 1 is, the maximum width becomes 4. So I can say that the maximum width for this given binary tree comes out to be 4, which I can definitely print. So I hope you have understood how to do a level order traversal and how to make sure that you do not end up having overflows. So guys, it's time to discuss the C++ as well as the Java code. As you know, the C++ code is on the left and the Java code is on the right. So it's identical, so you can definitely follow. You're given a root, right? And if the root is null, there will be no width. So you'll be returning 0. And what we will assign is an answer, which is going to store the maximum width. We're going to take a queue of pair. We're going to take the tree node and int. In Java, I have created this pair class. So what we will initially have q as the root and 0, and we are going to iterate till the q is not empty. So let's iterate till the q is not empty. And what we always did was whatever is on the q, we were taking it, right? So this for loop will be used for that. Like whatever is the size of the q, we're going to iterate on all the elements. Yes, we're going to iterate on all the elements. So what I have done is I have taken the first guy. Yes, whichever is the first guy, I have taken that index. So I have the minimum index possible on that level, right? And right after that, I made sure that the current index is nothing but, yes, current index will always be the subtraction via min. So basically, if it is having something as 2, I'll make sure that the current index is subtracted by the minimal, that's 1. Okay, so you can argue that it will always be 1, but it will not be. Imagine if you have a tree which is something like this. So in that case, on this level, this will not be starting with 1. This will not be starting with 1. It'll be 2. So the minimal on the level will always not be 1. It might be 2, it might be 3, it can be anything. So please make sure you subtract, okay, just in order to avoid overflow. So once you've subtracted, very simple, just take the node, and if there is a left, you take the node left, and after subtraction into 2 plus 1, after subtraction into 2 plus 2 for the right guy. Now always make sure you store the first guy and the second guy. Okay, store the first guy and the last guy. And right after this entire, like you have traversed for all the elements, you will have your last guy, first guy, subtracted plus 1. Compare with max answer, and at the end, return the answer, which is going to be your ultimate answer. Time complexity, since you're doing a level order traversal, it's going to be big O of n. Space complexity, you're using a Q data structure, so big O of n near about. So that is what the time complexity and space complexity will be for this particular solution. So I hope you have understood the entire explanation as well as the code. Just in case you did, please make sure you like this video, because it took a lot of efforts to make this entire tree series. Also, if you wish, you can definitely drop in a comment that will keep motivating me to make such further series. Also, if you're new to this channel, please do consider subscribing, because I'm going to bring in such more series in the upcoming future as well. With this, let's wrap up this video. Let's meet in the next lecture. Bye bye, take care.
Whenever your heart is broken